In this video, we'll be discussing the mathematical analysis of recursive and non-recursive algorithms. So we'll be starting with the general plan for analyzing the time efficiency of non-recursive algorithms. So here we have the 5-step procedure which needs to be followed in order to determine the time efficiency for any non-recursive algorithm. So the first step is to decide on the parameter or a set of parameters which indicate the input size. Then after the parameters are decided, then we'll identify the basic operation which is being repeated in the algorithm. Then we have check whether number of times basic operation executed can vary on different input of same size. So if it is true, then we investigate separately for worst case, best case and average case. Then fourth step is to select or set up sum expressing number of times the basic operation is executed. Then our fifth step is to, using standard formulas and rules of sum multiplication, either find a closed formula for count or at very least establish its order of growth. So in order to understand this general plan, we'll be calculating efficiency of 3 examples. The first example which we'll consider is of finding maximum element in a given array. So the problem says that we take an input of an array. So let's take an array A with input. I'll write the input here. So I'll write 21, 31, 45, 25 and 12 here. Here the size of array is 5 and indexing should start from 0, 1, 2, 3 and 4. Okay, so I've taken an array. Output should be the largest element. Largest element in array A. So my first step is to consider A0. A0 is 21, right? So I'll consider max value as 21 initially. Okay. Next, I should consider this loop for I is equal to 1 to n minus 1. N is 5, so n minus 1 is 4. So from I, we'll iterate from 1 to 4. Okay. Next, I have the other condition below here. It is if A of I is greater than max val. A of I means A of 1. A of 1 is greater than max val. So A of 1 is 31. 31 is greater than max val, 21. Yes. This condition is satisfied. If this condition is satisfied, then we need to update the max value. So max value would be A of 1, that is 31. So I have got the new updated value of max value here. Next, I'll update the value of I here. Next, I have A of 2. A of 2 is greater than max value. So I'll check here. A of 2 value is 45. 45 is greater than max value here is 31, right? 45 is greater than 31? Yes. So again, update the max value. That is A of 2 is equal to 45. Next, I have I value will update. I'll go to A of 3. A of 3 greater than max val. I'll check. So A of 3 value I have 25 here. 25 greater than max val is 45. Is this satisfied? No. When this is not satisfied, we can say that we have found the max value. When this condition fails, if condition fails, return max value. I have reached till here, right? Next, I'll also iterate to A of 4 and check. A of 4 is greater than max value. A of 4 is 12. 12 is greater than max value. No. So A of max value will be 45 only. So 45 would be returned. So this was about the algorithm part. Now we'll look into the analysis part. Okay. So as per the general plan, our first step would be to identify the input size. Input size here is n. Yeah, n value we have taken as 5, right? First is to identify the input size. We have written that. Second, we have to identify the basic operation. Here the basic operation is we have the comparison operation and assignment operation. These two lines are the basic operations. So comparison and assignment are the basic operations that has been executed. Next, third step is now I'll calculate C of n, that is number of times the basic operation has been executed. Number of times the basic operation executed. In order to calculate this, I can write C of n is equal to summation of, it starts from I is equal to 1 till n minus 1. So for loop I should consider, while calculating the number of times, I should consider the for loop. For loop here is I is equal to 1 to n. 1 would be the lower limit, n minus 1 would be the upper limit. lower limit, upper limit, and this, it has to repeat once, right? It has to occur at least once. So I'll write 1 inside. Okay. So now I have a formula that is, so if I have summation of I is equal to lower limit and here upper limit and here I have 1, then I can write it as u upper limit minus lower limit plus 1. So we should remember this for solving this problem. So substituting this formula here, I would get lower limit here, upper limit here is n minus 1, right? So I'll write n minus 1, lower limit is n minus 1, minus 1, and plus 1 is there here. So minus 1 plus 1 cancel, I'll be left out with n minus 1. So neglecting the constants here, I can write the C of n value to be equal to n minus 1 is there. So I can write it as n, or order of n, big O of n. So this is the analysis part. This is the time complexity, okay, which we have calculated. And we can also summarize that for best case, worst case, and average case, it will be the same, because it has to iterate through the n values, right? Because here we found the value at this position, but did we stop? No, we iterated throughout. No. So best case, worst case, and average case, all values are same, that is big O of n. So this was about a maximum element problem. Now we'll look into checking whether all elements in a given array are distinct or not. The second example. So in order to solve the second example, again, let's try the problem first. Let's understand the problem first. Second example is to check unique elements. So here input is, I'm taking an array A0 to n minus 1. Let me write the array here. So I've taken an array A. The input size is 4, but then 0, 1, 2, and 3. So it ranges from 0 to 3, the indexing. Next, the output is true if all elements in A are distinct, or it is false otherwise. So here we have I is equal to 0 to n minus 2. So I starts from 0. I'll write it here. I starts from 0 to n minus 2. N is 4 here. N minus 2 is 4 minus 2 is 2. Okay. I will range from 0 to 2. Next I have j. J is I plus 1. 0 plus 1 is 1 to n minus 1. 4 minus 1 is 3. J will range from 1 to 3. Now I need to check this condition. If A of I is equal to A of j, return false. Else return true. Okay. So let me write this. So I'll start from A of I. A of 0 is equal to A of 1. Is this satisfied? 10 equal to 20? No. False. Next, I'll update I value 1 I'll get, and here j value would be updated to 2. Here A of 1 is 20 and A of 2 is 5. This is also wrong. Next, I'll update I value, so I'll come to 2, and on this side I have j would be updated to 3. So here I'm considering I and here I'm considering j. So A of 2 is A of 3. 5 is equal to 3? No. 30? No. So none of the elements are satisfying here. So I can return true at the end. So this was about the algorithm part. Now we'll look into the analysis part. So for analysis, the basic input size is n. Yes, first step is done. Second, I'm doing the comparison here. A of I is equal to A of j, right? So this is the comparison part, basic operation. Basic operation is comparison, this line, okay, comparison. So here the worst case scenarios, there are two scenarios. So one is array with no equal element. Then other one is array in which only two elements are there, and two elements are pair of equal element. So pair of equal element. So this is about the worst case scenario. Okay, so we'll be considering the worst case scenario only here. So let me write the third step, that is to check whether number of times. Yeah, I have written the third step. Fourth step, to set up sum expressing number of times. In order to set up sum, for loop should be considered. So I have two for loops here. So I can write summation of I is equal to 0 to n minus 2 here. This is the first for loop, and second for loop I have is I is equal to 1 I is equal to j is equal to I plus 1, and on this side I have n minus 1, and with this equation should be repeated at least once, so I'll write 1 inside. So solving this, I have this formula, right? Upper limit minus lower limit plus 1. So let me solve the inner part first. So for solving the inner part, I'll get I upper limit n minus 1 minus lower limit I plus 1 plus 1. So n minus 1 minus I minus 1 plus 1. Minus 1 plus 1 cancel. Here I have n minus 1 minus I for this part. Now let me solve this part here. That is n minus 2 upper limit minus lower limit minus 0 plus 1. So here I get n minus 2 plus 1, n minus 1. So n minus 1 is outside. So n minus 1 outside, n minus 1 minus I is inside. So here I can, I can split it, or solving this further, I can n minus 1 minus I. So let me multiply these. So I can get n square minus n minus in and minus n plus 1 plus I. So this is what I've got. So neglecting the other constant parts, I have n square here, right? So let me consider the highest value, n square. So I can write that C of n value can be written as, here I'm considering the worst case, right? So I can write theta of n square. So this is for the worst case scenario for the unique element problem. I have got theta n square. So this was about the unique element problem algorithm. Now let's move on to the third algorithm, that is to perform the matrix multiplication. So in order to perform the matrix multiplication, we should remember how the matrix multiplication is done. So let me just quickly recall it. So if I have two elements, that is two matrices of 2 by 2 size, A and B, okay. So multiplication is done like this multiplied by this and this multiplied by this, for this multiplied by this for the first value, that is A00, and for the beside value A01, I'll write this and this 4 and 5, right? So I hope you know how to multiply it. So I'll write the value 6 plus 6 here, and here it will be 8, 4 2s are 8 plus 15. On this side I have 12 plus 4, and here I have 16 plus 10. Solving this further, I'll have 12, 23, and here I have 16, and here I have 26. So this is how the basic multiplication is done, right? So if I have to write the indexing, it would be something like 0 0 0 1 1 0 1 1. So it stands the same for A, B, C, all. So let me start with the analysis part with looking into the algorithm here. Firstly, algorithm matrix multiplication, we are taking A, one matrix, B as the other matrix. So it multiplies two square matrices of order n by definition based algorithm. So output should be C matrix. That is multiplication of A and B. So for I is equal to 0 to n minus 1 do. So this one I can write for I is equal to 0 to here n value is 2, right? So I'll write 1. So this is the outer loop, okay, to check the size of A. Next I have for j is equal to 0 to n minus 1. N is 2, so n minus 1 would be 1. So this is to check the size of matrix B. Next I have for k is equal to 0 to n minus 1, that is 1 again. This is to implement the basic operation. Next I have for k is equal to 0. So we'll start from for loop is considered here. Initially we are taking C of I comma j as 0 0 0 0. It is empty matrix, okay, null matrix, okay. So we'll start from k is equal to 0. So for initially I'll take k is equal to 0. Then this formula would be C of 0 comma 0 is equal to C of 0 comma 0, because initially I and j are also 0 0, right? Plus A of 0 comma, this k value is 0 here, this part, star B of 0, k value comma 0. So when you multiply all zeros, when you do this part, here we have 0 and A of 0 0 is 2. A of 0 0 is 2, and here we have B of 0 0. B of 0 0 is 3. I have the value of 6. Next, k is equal to 0. I am done. Now I'll take k is equal to 1. So again I'll write C of 0 0 is equal to C of 0 comma 0 plus A of 0 comma 1, because k value is updated here, star B of 1 comma 0. So previous C of 0, 0 value, I know it is 6. Here again I get 3 into 2, 3 into 2, this part and this part. So I'll get it as 12. So we require 12 here, we got 12 here. So now k is equal to 0, k is equal to 1. This k loop is done. So it will return back to this part. I will increment. I will become 1 and the same thing would be repeated again. So this was about the multiplication part. So we have understood how the algorithm works. Now we'll look into the analysis part. So here the input size comprises of 2 cross 2 matrix, right? So it is n cross n. Then the basic operation is this multiplication one. Now according to the basic operational count, I can write C of n as, here we have 3 for loops, right? So sigma, summation. First I'll start with I is equal to 0 to n minus 1, j is equal to 0 to n minus 1, and k is equal to 0 to n minus 1. And with all these, this particular basic operation would be repeated at least once, so I'll write 1 here. So solving this, first let me solve the inner part. So if I solve the inner part, I know the formula, that is to find the value, it is upper value minus lower value, u minus l plus 1, right, to find the value of summation. So I'll start solving this part first. So I'll get it as upper value, upper limit n minus 1, lower limit is minus 0 plus 1, n minus 1 minus 0 plus 1, minus 1 plus 1 cancel, so I'll be left out with n here. So I have got n from the outer part, that is k part. Now I'll consider the j part. J part again, it is n minus 1 minus 0 plus 1. So minus 1 plus 1 cancel. From the j part I've got n now. So I'll write n outside. And for I also it goes the same, n again outside. So if I multiply these three, I would get n cube. So I can say that the value, the C of n value is order of n cube, O of n cube, big O of n cube. Here the worst case, the best case, and the average case would all be same, because the multiplication has to be done, right? We need to check all the values from I is equal to 0 to 1, j is equal to 0 to 1, k is equal to 0 to 1. So the iteration happens for all the values. So this was about matrix multiplication. So here we have discussed the non-recursive algorithms. Now we'll move on to the recursive part, recursive algorithms. So in recursive algorithms, by the definition only we can understand that the value repeats, that the operations repeat. Okay, so speaking of the general plan for analyzing time efficiency, it is the same as that of non-recursive one. That is, all the 5 steps should be written here. So all the 5 steps should be written here. So here I have the factorial problem. So input is negative, non-negative integer, some positive integer. I can take 2 factorial, 2 as the input here, f of n. N value I'll take it as 2. Value should be n factorial. That is, if n value is 0, then return 1. Is n value 0? No. Else return f of n minus 1. That is 2 minus 1 into 2. 2 is outside. So this repeats. Okay, 2 factorial. What is 2 factorial? 2 into 1, 2. So I'll get 1 here. So again, this will go back here. F of 1. So f of 1, what is the value here? That is, and I've got 2 here, right? So f of 1 minus 1 into 2. 1 minus 1 is 0. So here this need not be considered. And when n becomes 0, it will return 1. So 2 factorial is 2 into 1, that is 2. So this was about the factorial algorithm definition. Now we'll look into the analysis part. Here we'll be making use of back substitution method. Okay, so in back substitution method, here one difference is that in the 4th step we'll be selecting the recurrence relation with appropriate initial condition for the number of times the basic operation is being executed. So let me start with the analysis part. My input size is n, and the basic operation here is f of n is equal to f of n minus 1 into n. So this is the basic operation. My 3rd step is the basic operation count is based on the algorithm basic operation setup. That is the recurrence relation here. This is the recurrence relation, right? Because it is being repeated till the condition is satisfied. So it will repeat once. Let me write m of n here. So I can say that this particular operation, it will repeat once. Yes. And along with that, it will repeat n minus 1 times. N value we don't know. So I can write m of n minus 1 here. So this is the recurrence relation which we have obtained by back substitution method. So it is very important to obtain the recurrence relation, because based on this only we can solve the problem further, right? So this step I have obtained. Now I'll substitute m of n value in this. Okay, so it will be 1, I'll write here, plus m of n value is substituted in n minus 1. So here it will be m of n minus 2 plus 1, right? So again I'll repeat the same, again substitute m of n value here, so I'll get 1 plus this 1 will come here, plus m of n minus 3 plus 1. So this will keep on continuing. So I can reach a stage where m of I is equal to I, because for n minus 3 we had got 3 ones, right? So for m of I can get I number of values here, that is I plus m of n minus I. So this is for the ith value which I have obtained. So generalizing this, I can write m of n is equal to n plus m of n minus n. M of n minus n value is 0, right? So I'll be left out with m of n is equal to n. So m of n is equal to n indicates that the function or the c of n value for this is order of n. So this goes the same for best case, worst case. It goes the same for best case and worst case. There's no average case we can consider here. So this was about a factorial problem. Now we'll look into the Tower of Hanoi problem. So Tower of Hanoi is a pretty simple problem, I would say. Yeah, understanding this, we have 3 towers, that is A, B and C. A has n number of disks here, so it needs to be shifted from A to C, A being the start and C being the final destination, and B is the intermediate value. So the conditions here are that the largest disk should be at the bottom and the smallest disk should be on the top. It should follow the same sequence as it was in the starting point. So, and B is the intermediate disk. So in one iteration you can move only one particular disk, and while storing the disks here, the sizes should be followed as being followed here. So the input is number of disks, arranging the disks orderly to the destination end C value. So if n is 1, so if I have only one disk, I can directly move it to C, right? So I need not go through B, the intermediate disk. If not, I have this recurrence relation is happening here, that is Tower of Hanoi, the same thing, n minus 1, n value, 1 value you decrease. Here I had 3 disks, now it will become 2 disks here, A, B, C. So A, B, C, the values are being shifted here. Next, A, B, C is being considered. From A I'll move it to C. Okay, so this is one condition. Else I can also write B, C, A. The values from B are shifted to C, and then B are shifted to A via C. C being the intermediate here. So this was about the algorithm part. Now let's look into the analysis part here. So I can write the input size as 3, and the movement of disks, let me consider the movement of disk to be m of n. Okay, so when n value is 1, I can directly move the disk right to C, that is only one movement is done. And when n value is greater than 1, then I can write here one movement should be there and here one movement should be there. So the 2 movements are happening here. Once I'll move, and I don't know how many times I'll again move, right? N minus 1 times. This is for this part, ABC part. And coming to this BCA part, again I have 1, and here I have n minus 1. So this one I can write it as m of n is equal to 2 times of this. This equation is being repeated twice, right? So I can write 2 times of m of n minus 1 plus 1, right? So now this now that I have obtained the recurrence relation, I'll apply the back substitution method here, and let me solve the problem now. So let me consider this part when n is greater than 1. So I'll start solving this. So I'll write m of n is equal to 2m n minus 1 plus 1. Now let me substitute m of n value in this part. So if I substitute m of n value here, I'll get 2 again being repeated here. So I'll write 2 here, m of n minus 1 minus 1. So it will become n minus 2 plus here plus 1 was there, again plus 1. So it will become 2 here, and the external one remains as same. So next I'll again substitute m of n value here. So I'll have 2 and 2 of m of n minus, here 2 was there, again minus 1, so it will become n minus 3. Here 2 was there, plus 1 is being considered here, so plus 3. Here plus 1 would, here I'll have plus 2 because above 2 plus 1. So if I club this, I can write it of the form m of n or m of I for ith value. If I'm repeating the same operation for I number of times, I can write it as 2 times of I, and inside I'll write m of n minus I plus 2 power I minus 1 plus 2 power I minus 2. It goes on till 1 and so on. Let me consider this as equation 1. So if I assign n minus I as 1, this part if I assign it as 1, I can take I value as n minus 1. So let me write I value as n minus 1 here, and let me check. So m of n is equal to 2 times n minus 1. Here inside it is n minus n minus 1 because I value I am substituting, right? This bracket close, plus 2 times n minus 1 plus 1. So again solving this further, I can write m of n is equal to 2 times n minus 1, m of 1 value I know it is 1 only. So this particular thing I'll get 1 only. N minus n, plus n minus n, cancel, 1 I'll be left out. Minus 1, it will become plus 1. So I got m of 1 here. Plus 2 times n minus 2 plus 2 times n minus 3. It goes on till plus 1, and this is the second equation which I have obtained. So, okay, second equation I can simplify it further, which can be written as m of n is equal to 2 times n minus 1. M of 1 value is 1 only. So plus 2 times n minus 2 plus 2 times n minus 3, so on till plus 1. This is my second equation. So I've got first equation, second equation. So I'll multiply second equation into 2. Then I'll get the third equation, that is m of n is equal to 2 power n plus 2 power n minus 1 plus 2 power n minus 2, so on till 2. This is my third equation. So if I subtract 2 minus 3, I would get m of n is equal to 2 power n minus 1. So this is the exponential function. Here I can write that the time complexity would be order of 2 power n. So it will come under the worst case. The worst case would be when expression is cubical, quadratic and exponential. Here it is exponential, right? So it will come under worst case only. So here also it came cubical, no? So it is worst case. Okay. So this was about Tower of Hanoi problem. So if you go through this, the steps, you can easily follow. Speaking of the back substitution method, it is a bit difficult, but then when we'll discuss the Master's theorem in the upcoming modules, it will become very easy to calculate the time complexity. So let's move on to the third example here, which we have is binary recursion. So binary recursion, the algorithm is binary. We take an input n. So the number of binary digit in n's binary representation. If n is 1, then return 1, else return binary recursion. This is floor function, okay. So it is will be rounding off to LHS value plus 1. Okay, we'll look into this with an example. So let me take n is equal to 3. So if n is equal to 3, binary of n by 2 plus 1. So this part I can write 3 by 2. This is called as floor function. That is 3 by 2. 3 by 2 is 1.5, right? But I'll substitute it to, so I'll get 1.5 here. So here I have 1, here I have 2. Which one will I choose? So if I round off, I should choose the LHS part. That is called floor function. Okay, I'll be selecting 1 here, 1 here. And 1 plus 1 is 2. So for n is equal to 3, I get 2 binary representations. Okay. So it goes the same for, let me take n value as 10. Okay, so b of floor function 10 by 2 plus 1. 10 by 2 value, what is 10 by 2 value? 5. So 5, I'll again do this part, substitution part. So floor function of 5 plus 1. So this can be written as b of floor function 2 plus 2. So 2 by 2, I get 1 here. So again, substituting this again, so I get 2 plus 1, 3 here. This again, yeah, so I'll be left out with 4. So n is equal to 10. 10 has 4 digits, right? 4 values, right? Binary values representing. So this was about the binary recursion algorithm. Now we'll look into the analysis part. So the number of additions made in computing binary recursion, that is floor division of n by 2, is a of n by 2. So a times floor division n by 2 is computed, right? So I can write a of n value as a of floor division n by 2 plus 1. The same formula, I'm writing it here for n value greater than 1, because if n is 1, we'll return 1 directly, right? So there are no additions, further additions here. So for a of 1 it is 0, and for a of n greater than 1, I can write it as a of floor division of n by 2 plus 1. So I'll start solving this now. So I have a of 1 is equal to a of floor division n by 2 plus 1. Now I'll substitute a of n by 2 here, that is a of n by 2 square plus 1. So if I substitute this, I'll get a of 1 as a of floor division n by 2 square plus 1. This is the internal part. Externally, I'll be having 1 here, right? So if I add these two, I can get a of n by 2 square plus 2. So I can write it as a of n by 2 square can be written as a of n by 2 cube plus 2 plus 1. Further, n by 2 was taken, now I'll take n by 2 square. So if I take n by 2 square, 2 cube will be there here, and 2 previous 2 and plus 1 again new. So this keeps on repeating. So let me take for ith element. So it will be a of n by 2i, 2 to the power I plus I. So I can take, I'll take n by 2 power I as 1. Then I can write I value as log n, right? So further I can write the formula a of 1 plus log n as 0 plus log n, because a of 1 value I know it is 0 here. So I'll write log 1 here. So I can write for a of n, I'll be left out with log n, right? So log n being a logarithmic function. So the time complexity, I can write it as log square, log to the base 2n. So this is the time complexity for binary recursion. So I hope you have understood the analysis for recursive and non-recursive algorithms. If you have any doubts, do let me know in the comments, and subscribe to my channel. Thank you.